Welcome everyone. Today we're going to keep talking about partial fractions, but we're actually going to see how to integrate once we've done a partial fraction decomposition. So in this lesson we're going to see how partial fraction decompositions are really going to help us integrate those rational functions. And so we know with a partial fraction decomposition there's a few different forms that we regularly see. And so there's going to be a few different integrals that we're going to see on a regular basis as we integrate these partial fraction decompositions. So the first two integrals on this list really come from the linear terms in our partial fraction decomposition. So these two really are going to come from those linear terms in our partial fraction decomposition. And the last two, these we're going to see because of an irreducible quadratic. All right, so let's look at these four integrals. And as we get into it, it's going to be, we're not going to prove these, but it's something you can do, and it's, I recommend that you do it because we have you've seen the techniques at this point to prove each of these integrals, and you can do that with a u substitution. So that might be good practice. So let's look at the first one. What does it say? We're looking at the integral of 1 over kx plus d, where k and d are just constant terms. And when we integrate that 1 over function, that becomes our natural log. So it's going to be the natural log of absolute value, what's in the denominator, so kx plus d, and that stays unchanged. But then we take that constant that's in front of the x, we flip it and put it in front. And really where this is coming from a u substitution where we would let u equal the term that's in the denominator. So we'd let u equal kx plus d, and then du would be k times dx. And then you'd go through the u substitution process. So there's some more work in here. But this is an easy enough substitution. We're going to see this a whole bunch of times in our integrals that are coming up. So this is probably a formula to just have memorized or just to remember what the process is. Same thing for the next one. Here we have the integral of 1 over kx plus d, but now that entire denominator, it's not just kx plus d, it's kx plus d raised to a power. So we would see this when we have a linear term that has a greater multiplicity, greater than 1. So how do we handle this? Well, again, it's another u substitution. So we'd let u equal the exact same substitution, kx plus d. Differential would be k times dx. And so you can see where that 1 over k is coming from in front. It's just coming from our differential. And really, you can remember this formula, but I probably wouldn't. This is just power rule. So it'll probably be easier just to see this one in action, and we'll see that in an example. So really, this is just power rule here. And the only thing tricky is when we have this power of n that's in the denominator, we need to convert it to a negative exponent. So that's why this is looking a little different. We have this negative n because it's a negative exponent since it's in the denominator here. All right, so another one we're going to see is the integral of x over x squared plus a squared, or really just any constant here. It doesn't have to be like an a squared, as long as it's positive. So, think of this a squared as really emphasizing that we have x squared plus a positive constant here. And this is another u substitution. So I told you, you could do all these with u substitution. You would let u equal what's in the denominator, x squared plus a squared, and then du would be 2x dx. And if you're comparing, we have an x dx in our integral, we have an x dx in this differential, but we have this extra 2. What would we do? Divide both sides by it. So we end up with a 1/2 in front. And it's really coming from this extra constant that we have here. And then we have the natural log of absolute value x squared plus a squared. And then our usual plus c at the end. And then finally, the last one we're going to see from primarily from irreducible quadratics is this 1 over x squared plus a squared form. And this one you probably just have to memorize. So it involves arctan, the inverse tangent function. And we have to identify this constant here. And it's 1 over a times inverse tangent of x over a. And so the way you can figure out the constant to put here is you take this a squared and you do the square root of it. And then that's the number that you're using inside this integral here. So you look at the number, it's positive, you can do the square root of it, and then whatever that square root is, that's what you're putting in here. This one can also be proved from a u substitution, and the special case of this, we've seen this type of form before. The special case of this is when this is just a plus 1 here. And we know that's just inverse tangent function. So now we're seeing what happens if we have a different constant other than a plus 1. How do we integrate that? So notice these two integrals look pretty similar from the third case here and the fourth case here. The only difference is we had this x in the numerator. We don't have that x here. And notice how different the antiderivatives are. So that's just something to keep in mind when you're doing these. So we're going to see these 4 different integrals pretty regularly. So let's try an example. Let's look at example 1. And here we're going to integrate the function 2x plus 5 over x minus 1 times 3x plus 4. And we've seen this function before. This is a rational function, and we actually did the decomposition. So that would be really our first step here would be to do a partial fraction decomposition of this function. Now, we've done that in a previous example. So what was that decomposition? It was 1 over x minus 1 minus 1 over 3x plus 4. So we've done that partial fraction. That's where all the work is. So we've kind of done all the work beforehand. Now the integration, the actual calculus part of this is basically just referring back to that last page and figuring out the antiderivatives. So there's really not going to be too much work here. All of our work was done with this partial fraction decomposition. All right, so how do we integrate this 1 over x minus 1? And how are we going to integrate this 1 over 3x plus 4? Well, let's go back to the other page. And we're talking now in this first form. It's just 1 over a linear term. There's no higher powers. There's no irreducible quadratics. It was just all distinct linear terms. So how do we integrate this 1 over x minus 1? Well, it's the natural log of the absolute value of the denominator. And then technically, we would look at that constant in front of the x, flip it and put it in front, but it's just a 1. So when we do the reciprocal of 1, we end up with 1. All right, now we go on to the next fraction here. It's 1 over 3x plus 4. We're subtracting. So it's, again, that 1 over kx plus d form. So it's going to be the natural log of the absolute value of what's inside. We don't change anything. We'll put our plus c while we're at it there. And now we actually do see a constant in front of the x. So we take that constant, flip it, put it in front of that natural log. And there we go. We're done. So not too bad. Really, all of the work for these problems is, it's not calculus related, it's, algebra. So all of the work, all of the heavy lifting was done with this partial fraction decomposition, and then the integration is it's basically just a one-liner. We get it done in one step. Let's try another one. I think this was going back to our last learning outcome. This was, I think, 2 lessons ago. This was example 2, where we actually went through the decomposition. All right, let's try the next one. So here we have the integral of 1 over x squared minus 25. Now notice for this one, it's a minus. So if we go back to our list really quick, these two forms involve a plus a squared. The one we're looking at, has a minus. So these, remember, were our irreducible quadratics. The x squared minus 25, we can actually factor that, and it turns out we did. We factored that. We did the whole decomposition already. So this was, I think, example 3. So this denominator, because of that minus, we could actually factor this further. And what was our decomposition? It was 1 over 10 over x minus 5. So that 1 over 10, just think of it like a constant. If you want, you could write it as a 1 over 10 in front, however you want to deal with that. Then we have minus 1 over 10 over x plus 5 dx. So that was our partial fraction decomposition. And we saw how to do that back in the last lesson in example 3. We went through all the steps there. So most of the work for this problem was done already in that partial fraction decomposition. All right, so this is again 1 over a linear term. So the actual integration is just going to be one line. It's going to be one step. We can just do this. So the 1 over 10 is a constant. That's just going to be in front. And then, if you want, you can think of these as maybe like this last one here. You could also think of these as like 1 over 10 times 1 over x plus 5. Maybe that's a little easier to see. And so the 1 over 10 is just a constant multiple, so it's just going to stay in front. And then how do we integrate that 1 over x plus 5? Well, it's going to be the natural log of the absolute value of, well, we're doing the x minus 5 here. And then there is a constant in front of that x, but it's a 1. So normally we would put 1 over that constant, but 1 over 1 is just 1. So for this first fraction, the 1 over 10 is a constant multiple, so it goes in front. And then the integral of the 1 over x minus 5 is just natural log absolute value x minus 5. Same thing for the last one here. We have a minus 1 over 10. And then what's the antiderivative of that 1 over x plus 5? Well, it's just the natural log of absolute value x plus 5. And then normally we would take the constant in front of the x, flip it, put it in front. But again, it's just a 1 there. So when we do the reciprocal of 1, we get 1. So we don't write it. And then plus c. And there we go. We have our antiderivative. Now there's a little bit, if we really wanted to have fun, we could probably do some log properties to rewrite this even further. But in terms of just getting the antiderivative, perfectly fine. All right, let's try another one. We're on a roll. So it really helps to have all these partial fraction decompositions done. The actual integration is not too bad. Let's look at example 3. So we're integrating 2x squared minus x plus 4 over x cubed plus 4x. Again, this is a rational function, and this is one we've already done. So you can see how the denominator is going to factor. It's going to factor into an x and then an x squared plus 4. So we're going to end up with an irreducible quadratic. And we went through the partial fraction decomposition for this one already. So this was back in the last learning outcome, and this was, I believe, example 4. So we already did all of the heavy lifting calculating the partial fraction decomposition for this one. So that would be a key step here, where most of our work is going to be, is actually doing that. So let's summarize the result. What did we find? Well, we found that it broke apart into 1 over x plus x minus 1 over x squared plus 4. So that was our partial fraction decomposition, and we did that in the last lecture. All right, so we have that. Now we want to integrate. Now we have this irreducible quadratic piece here, and the way we handle these in general is we're going to split them up. So looking at this numerator, we have this x minus 1. We're going to split that up. So we're going to split this up further. And how we're going to do that is we're going to write it as, well, we'll still have that 1 over x, but then we're going to take this x and divide it by x squared plus 4. And then we're going to take that 1 and divide it by x squared plus 4. So we can always split up fractions like that. And the reason why we do that is this first fraction has an x in the numerator, so we have x over x squared plus 4. The second fraction here has a 1 over x squared plus 4, and those are the two different forms for these irreducible quadratics. So if we go back to our first list, keep in mind what we have: x over x squared plus 4 and 1 over x squared plus 4. If we go back to our list here, we're talking about these two cases. So one of those fractions has an x in the numerator, the other one has a 1. And so how we actually do their antiderivatives is pretty different. So the one with the x in the numerator ends up involving the natural log. The other one, the one with the 1, ends up involving inverse tan. So let's see how we're going to do this. All right, so let's start with the easy one. 1 over x, that's just natural log absolute value x. Don't forget the absolute values. What about that second one, the x over x squared plus 4? Well, that's also going to be natural log of absolute value, the denominator, x squared plus 4. Now, technically, we could drop the absolute value here because x squared plus 4 is always positive. It's always greater than 0. But because we're doing u substitution here, we also have a 1/2 in front. And we saw why when we were looking at the formula. So this is just the formula for these cases where we have x over x squared plus a constant. All right, now what about this negative 1 over x squared plus 4? Well, that's going to involve arctan. And let's write out the general format here, just to remember. So we have 1 over x squared plus a squared. And the integral is 1 over a times the inverse tangent of x over a plus c. So how did we find a? Well, we take that constant term and we do the square root. So that's what we're going to do here. We're going to look at that constant term. It's a plus 4. And a is going to equal the square root of that plus 4, which is just going to be 2. So when we apply this formula for the integrating this third fraction here, we're going to end up with minus, because we're subtracting, 1/2. So that's coming from the 1 over a. and then inverse tangent of x over 2. And then plus c. So we figured out a, and then we just plug that into this formula essentially. And that's how we're getting the antiderivative. And there we go. So it requires a little bit more work when we have these irreducible quadratics. So this is the general strategy for when we have an irreducible quadratic, is to break it up further into those two separate fractions, because when we have that x in the numerator, we integrate it one way. For that constant term in the numerator, we integrate that fraction pretty differently, involving inverse tan. So that's a kind of one of the little key strategies here. We have to split up that fraction just a little bit further. All right. So it helps to have all these partial fraction decompositions done. Let's try one more. And this is another example that we've seen before. So the integral of x to the fourth minus 2x squared plus 4x plus 1 over x cubed minus x squared minus x plus 1. It's a rational function, but this one, there were a few things here. So, there were a few things going on. And the first thing we had to do was we noticed that the degree of the polynomial in the numerator was larger than the degree of the polynomial in the denominator. So we actually had to do some long division. And then we could do the decomposition. So what did we end up with? Well, after everything, we did this one before. This was, what example was this? I think this was example 5 in the last lecture. So just go back to what we did yesterday, and you'll see us go through all these steps for the decomposition. We also had to do polynomial long division. So what did we end up with after everything? Well, we ended up with x plus 1. So that really came from the polynomial long division. And then we had our partial fraction decomposition. 1 over x minus 1 plus 2 over x minus 1 squared plus, minus 1 over x plus 1. So, just kind of diagramming this out a little bit, the x plus 1 here, that came from our polynomial long division, if we remember back. So we had to do that before we could do the partial fractions, because the degree of the numerator was greater than the degree of the denominator. And then the rest of this was the partial fractions, the partial fraction decomposition of the remainder term. So what we had left over from our polynomial long division. We were able to do a partial fraction decomposition there. Just abbreviated that. All right, so that one took a little bit of work. So we've done, like we've seen, we've done all the heavy lifting here in terms of breaking this fraction apart into easier to work with, easy to digest pieces here, essentially. These are going to be easy to integrate. So let's do it. Let's integrate this. It's not going to be too bad. Integral of x, yeah, we can do that. 1/2 x squared. Integral of 1, sure, plus x. All right, now let's get to maybe some interesting things. What about the integral of 1 over x minus 1? Well, that was just one of our linear terms. So it's just going to be the natural log of the absolute value of x minus 1, the absolute value of the denominator. We don't change anything. Now, normally we would take a constant that's in front of the x, flip it, put it in front, but we just have a 1 there. So nothing showing up. Sometimes it does, though. And we're adding. All right, let's go on to the next fraction. And let's actually do this one. We'll work this one out, because this one is going to be the trickiest of the bunch here. So let's actually work this one out. We'll try it down here. let's see how we would do this. And once you get the hang of these, you probably can do it mostly in your head. Maybe you have to show just the conversion to the negative exponent. So we're going to rewrite this with a negative exponent. And then once you have that negative exponent, it's power rule. So the 2 is a constant multiple, so it just stays in front. We're going to keep the term inside the parentheses exactly the same. Then we're going to add 1 to this exponent, so that's going to take us up to -1. Then we take that new exponent, we flip it, put it in front, and there's our antiderivative. Now, if there was a other constant in front of the x here, we would have 1 over that constant in front as well. But we don't. So how does this simplify? We end up with just -2 times x minus 1 raised to the -1 power. And just because everything's in fractions, let's convert this back to a fraction. Just looks nicer. So we could write that as -2 over x minus 1. Perfectly fine, though, if we wanted to leave that with a negative exponent. And then we have a minus, and then we just go on to our last one, and this is just the natural log of the absolute value of x plus 1. So just do the natural log of whatever's in the denominator. That goes inside your log function. And if there were a constant other than 1 in front of the x, we would flip that and put it in front. So there we go. Doing all of that partial fraction decomposition, that's the hard part for these. The integration really is not too bad. Let's just try another one of these, just slightly different, just to see how it looks. So let's, as just a little practice here, this isn't what we had, but it's good just to practice. Let's say we had 1 over 3x minus 4 raised to the 5th power. How would we do the integral of that? Well, we would write it as a negative exponent, so 3x minus 4 raised to the -5. Again, this has nothing to do with the example we just did, just getting a little extra practice here. Now we want to do the power rule. So we keep what's inside the parentheses exactly the same. We take this -5 exponent, we add 1 to it, so that takes us up to -4. We take that new exponent, which is -4, and flip it, put it in front, so -1 over 4. And because this was in that form kx plus d, so this process only works if it's that format, kx plus d, because we have this constant multiplying the x, we're going to take that constant 3 and we're going to flip it and put it in front. So we end up kind of with two fractions in front there. And then to simplify this, we can just multiply those together. So just to get a little bit more practice with those fractions where it's 1 over a kx plus d, but then it's raised to a power. So really the key step here is write it as a negative exponent. All right, so that's really it. The partial fractions is really the main star of all of this. The actual integration is not too bad. So really what you want to do for these examples is you want to have these 4 important integrals, probably have them memorized, or at least have them in a place where you can refer back to them, because you're going to be doing these quite a bit, especially when we're integrating these rational functions. All right, so we're going to stop there for today, and we will see everyone tomorrow. Have a good rest of your day. Bye-bye.